Okay, welcome back. So we are in the last week of this course now. So this is the week 8, and as I mentioned towards the end of the previous week, so during this week 8 we will be mostly focusing on kind of revising the material, whatever we have covered earlier. Then I will give you a lot of examples. That's the plan for this week, is to go over several examples from different fields, some research projects, some industrial projects, in terms of how this LCA tool is used in real world projects. So if we get started, that's like a big picture where we have been looking at in terms of, this is kind of the summary of what we have talked so far in a very simple form. If you remember, we looked at life cycle stages. We talked about the system boundary. So here what you see in this picture is from different boxes and a very simple schematics. Again, whenever you are doing any of these pictorial descriptions, you don't have to be an artist to do that. Even if you make the boxes like this and put all these different inputs and outputs, as you can see over different arrows for the material and energy coming into each of the unit process, as well as whatever is the output in terms of the waste product. So all these, if you just depict in this particular form, that's more than enough to give a good pictorial description of any process. So as you can see here, we start from raw material acquisition, raw material extraction, then material processing, product manufacturing, use, reuse, disposal, and we have talked about this many times in this course so far. So this being the last week, you should have I'm pretty sure you must be very conversant with this material so far, if you have gone through each and every of the video that we have produced. So for each of this process, we have the material and energy input, and we have the waste as output. So this is what we had looked at earlier. We had this input parameters, which was a material, energy. When we say material, it could be the raw material, metals, non-metals, it could be the organic material, it could be even, it also includes water. So we talked about the water as well, the water footprint. So for all these stages, we need certain materials going into the system and certain waste being produced. And we took this waste being produced, and what we did that, if you remember what we did with that is we produced, we had several, we looked at, okay, what are the emissions coming out? So what would be the environmental impact? What would be the human health impact related with these emissions? And they lead to these, what we call them, the midpoint indicator. As you see towards the bottom of this particular sketch, if you look at that sketch again, if towards the bottom of the sketch, you can see that what we call them the midpoint indicators. Midpoint indicator means whatever is the exhaust coming out. Exhaust, when I say exhaust, these are not, it's not vehicular exhaust we are talking about. I am using it in a more general term. It's any emissions coming out from the process, and that emissions could be air emissions, could be water emissions, could be waste emissions, and all these had certain environmental and human health impacts, and that's what we have categorized towards this end of this sketch, which we call this midpoint indicator. And the midpoint indicator leading to global warming, ozone depletion, smog, acidification, ecological harm, and there are several more, with only few are listed here. And then from this midpoint, we go to the end point, which is the human health and ecosystem damage, because at the end of the day, what we are interested is any industrial activity, any process that we are proposing, or we are undertaking, or we have been using for last several years, what is the human health impact, what is the ecosystem impact, and how to reduce that. So this whole LCA exercise helps us to identify the impact, and then once we have identified the impact, we can always go for how to mitigate that. So before you go for the mitigation step, you need to understand, and this is what in this particular sketch, in a very like a nutshell, gives you the big picture of this whole course that we have been talking about for last 7 weeks, and this will be the last week of the course. So whenever you look at any of these emission event, there is one example here, that if you are looking at the emission event, one very common example that we have been using is chlorofluorocarbon. Chlorofluorocarbon, if you remember from this old refrigerators that we have been using in our houses, the fridge that we call in more common language, refrigerators used to have chlorofluorocarbon. now we don't use it anymore. The CFCs have been kind of, you can say, phased out from use in refrigerators. And why they were phased out? Because we were concerned about ozone depletion. So CFC, how it was used to happen. So if you, that's what has been explained in this particular sketch over here. You have this chlorofluorocarbon emissions from process, and that goes into, it gets into the environment, it gets transported in the environment, transformed, and it goes to the stratosphere. And what it does, it releases chlorine. It's a chlorofluorocarbon, so it is has a chlorine there. So it releases chlorine, and that chlorine leads to ozone destruction. So chlorine reacts with the ozone, and it basically reduces the ozone layer. So what is the importance of ozone layer in our stratosphere? All the UV rays or the harmful rays that is coming from the sun, what the ozone layer does, it either absorbs those harmful rays, or it reflects it back. So if this is the ozone layer that you are looking at, so the light ray coming in from the sun, so if all the harmful effect will be absorbed in this layer, or it will be sent it back into the atmosphere. So when it doesn't come into the lower part of the atmosphere where we live or where the plants are, so we are not getting the harmful effect of all those harmful UV rays. But if the ozone layer, this is the thickness of the ozone layer, if it gets thinner and thinner and thinner, what is happening, that the harmful rays is able to penetrate through that, and it will come out at the bottom. And when it comes out at the bottom, it will have we will have more skin cancer, we will have impact on our plants and all those. So that's where, so with the depletion of ozone, we are losing ozone in the stratosphere, and because of the loss of ozone in the stratosphere, we calculate that as a ozone depletion potential. That's we call it as a ozone depletion potential. What is the ozone depletion potential? Because of the CFC release. So that's our midpoint indicator. But midpoint indicator is basically all these midpoint indicators that we have talked about. That basically gives us to a kind of a way to calculate what is the kind of immediate impact, or what is the impact which is happening to the different species available in the atmosphere. But ultimately we are going from this midpoint to the end point, and this end point, as you can see in the next box below that, end point damage is increased UV radiation leads to the following damage. And what kind of damage? Is skin cancer, crop damage, immune system, damage to material, marine life, cataracts. So these are our end point damages. So think about that, because of the CFC release from the refrigerators, going into the atmosphere, creating ozone layer depletion, and potentially leading to having more skin cancer, more crop damage, immune system suppression. So this is what we are able to calculate. Of course, there are a lot of I would say guesstimates there. There are lots of modeling which went into all these exercises, but this tools like LCA gives us that's a very powerful tool, because even if it may not be 100% perfect, no tool, no environmental model is 100% perfect, but at least it gives us some idea of what could be the potential in environmental impact and the human health impact, and that leads to kind of a better design. We can go for more eco design, more green engineering, pollution prevention, and all those things can come into picture. So on the right hand side, you can see the arrow kind of shows you the environmental cause and effect chain. So what we can do now, once we reduce this, we will have less impact over there. So we can go for mitigation of these kind of exercise. So what I have said so far in this video kind of summarized in a couple of slides over here. So don't worry too much about going through the line by line on these slides. You can read it later on. We will have this material available for you as you can see from the previous weeks as well. You have seen that the materials are available for you. This is for your reading material. Don't worry too much going line by line of these slides. Essentially what we are trying to say here is we look at the emissions, we look at the input and output, and that's the inventory. Which based on which we do the environmental impact indicators. And so this inventory when we got this inventory, they do not characterize the environmental performance of the product. We have to look at what kind of, because overall we have to look at what is happening in terms of effect on the environment. Say if you get an example, say if we have a 1 kg of lead, or a certain amount of lead is emitted to the atmosphere, it will have a different kind of impact as opposed to 1 kg of iron being emitted to the atmosphere. So 1 kg of lead going into the atmosphere or to the water versus 1 kg of iron going to the atmosphere, the effect is different, because the way this iron or lead or say arsenic or cadmium or any organic chemical, how they will react in the environment. What will be its fate and transport in the environment? What is its toxicity in the toxicity in terms of that particular chemicals or elements present there? That dictates what will essentially happen in terms of its impact on environment as well as the human health. So what we have, so we have to have an overall characterization of the environmental performance of a product or process, and we use this life cycle inventory data for doing that. So that's we have, so this is divided. So when we try to do this classification or this impact assessment, they are usually divided into 3 major steps. One is we have to do the classification. Classification means where input and output, whatever is during the inventory process, which I have explained earlier, we classify them into different environmental categories. For example, methane, carbon dioxide, CFCs, they have been classified as global warming gases. So not each gas has global warming potential. So like not a, so whichever gas has a global warming potential, we will put them as global warming gases. Whichever can cause acidification, we'll put them in acidification column. Eutrophication, similarly damage to in terms of like a salinity. So you can pick different categories as we had those environmental impact categories, and we can club these emissions in those categories. What happens in some of the cases where you may have one particular emissions which may have impact on 2 or 3 different categories. So how will you do that? In that case, what we do, we take a weighted average. We kind of decide based on this emissions coming out of this, 40% will go there, 30% will go there, another 30% will go there, and we decide based on that particular category. So classification is when you have the input and output, whatever is coming out, we classify them into different categories, and then you will see some examples of that. Then after you have done, we have to have the characterization, because what is the relative potential? And if you look at the global warming potential exercise, what is it? Say carbon dioxide is also global warming gas, methane is a global warming gas as well, CFC has global warming potential, nitrous N2O has global warming potential. So, but how much? How much is the global warming potential of each one of these? So, to solve our problem, what we have done is we have taken one particular gas or one particular element or one particular component of these different like emissions coming out for different categories as one unit. So what does that mean? So for example, in global warming potential, we have assumed that whatever is the global warming potential coming out of carbon dioxide gas, that is 1. So that's 1 is the global warming potential for CO2. So based on the CO2, what would be the global warming potential of methane, CFC, nitrous oxide? So we have a number. So CO2 becomes our baseline for global warming potential. So that's how we have done this characterization. So we calculate the relative global warming potential. Then you go for valuation, where the relative importance of each environmental impact category is assessed, and a single because again, as I said earlier as well in some of the previous videos, that if you give all these different numbers to a I would say to a policy makers, and say you are doing a presentation in front of the environment minister, either at the state level or at say in Delhi or at the federal level in any country where you may be, and if you are doing this presentation and you come up with all these complex equations and so all these complex graphs, and then the people, the scientific community will probably understand what you are talking about if you present it well. Think about the minister who may not have that much of a scientific background. So to make him or her understand the significance of that, we need to bring it down to a number which makes certain sense, and that number should be relative, so that we can say this is better than like if among the two, if we are comparing, we can put the number. And again, this is similar to air quality number or the water quality index, or to certain extent even the stock exchange index. So we come up with this valuation where the relative importance of each environmental category is assessed, and a single index for environmental performance can be calculated, and we will look at some of these examples in a minute. So in terms of classification, there are, as I said, there are different impact categories. Global warming we talked about, then you have the we talked about ozone depletion as well. There could be photochemical smog, human carcinogenity, atmospheric acidification, aquatic toxicity, terrestrial habitat destruction, depletion of. So there are a lot of categories which is there, which based on what kind of emissions coming out, we can find out whether they are going to impact either one of these categories. So that's. So now let's look at an example. So if you have as an example of classification, say if you take air emissions for a study that if you take air emissions from a study which compared glass and polythene, which is given in the table below. This is the selected emissions from the product of 1 kg of polythene and 1 kg of glass polyethylene. So what are the emissions coming out per kg of polyethylene? We have the nitrogen oxide, sulfur oxide, carbon monoxide. So these three material, again, these are not the total list. This is the list. This is the list coming like just some example parameters. So these are the kg emissions per kg of polythene. Then, okay. So let's look at an example for classification where we will be looking at the air emissions from two processes. So say for the production of polythene versus production of glass. So as you can see in the table on the right hand side at the below here, what it presents as kg emissions per kg of polythene of in one column, and the other column is kg of emissions per kg of glass. And we are looking at three selected air emissions. As I said, these are not the exhaustive list. This is the three emissions that we are looking at: nitrogen oxide, sulfur dioxide, and carbon monoxide. As you can see from the figures, for nitrogen oxide and sulfur dioxide, we see more emissions in glass as opposed to for per kg of polythene, where in carbon monoxide it is different. We have less coming out from glass and more from the production of polythene. And these here, if you look at nitrogen oxide is it will create photochemical smog, will create global warming, acid precipitation, acid deposition. So that's what nitrogen dioxide is predominantly involved in. Carbon monoxide, on the other hand, was especially for the smog. It's not a greenhouse gas. So you can look at different types of emissions comes out from industrial process. It doesn't mean that one particular type of industry emissions will be same irrespective of the different industrial process we'll look at. For some of the emissions will be more depending on the type of operations they are there, and as opposed to other, as we saw over here, nitrogen dioxide and sulfur dioxide was higher for polythene, higher for glass as opposed to carbon monoxide, which was lower. So what does that all these mean? So if we take all these data and then we want to have some relative weights to them. We assign some relative weights, so that, and based on the potency of different types of emissions, energy use, material use. So we put some, we give them a potency factors, and this potency factors needs to be established. So these potencies reflect the degree to which the inventory elements contribute to environmental impact. For example, if its environmental impact is global warming potential, and so we look at different relative impact of emissions of different global warming gases. And as I said earlier in this video, and for global warming potential, we have used carbon dioxide as the baseline. So for carbon dioxide, we take it 1, and for other gases, based on carbon dioxide, how much more or how much less. So that's what we kind of. So once this potency factors are established, we can take this inventory values for input and output and combine with this potency factors, and we reach to impact scores. And I'll show you in how this is done in a mathematical way. So the general form of for the dimensionless environmental risk index, we calculate that based on whatever is the emission factor, what is the emission potential, plus the inventory emissions coming out, and for different processes. Here B stands for the benchmark compound. So here and the I is the chemical of interest. So to estimate the indicator I for a particular impact categories, due to all the chemical release from the product system, we must sum them. So we take this dimensional risk index, and risk index here is here I is for that particular I chemical, the chemical number I, or we can have and the B is for your baseline. So you divide. So here in terms of global warming gas, this will be our carbon dioxide, and whatever is the emission potential and the impact coming out from the other emissions, for example, say nitrous oxide, for methane, and that will go on top, and we take this ratio, and that ratio multiplied by the mass of that particular chemical being released. So, that is what you see over here. So, if you do a total impact categories, when we go for total impact categories, of course, we have to do the summation, and what will sum? Will sum this dimensional risk index multiplied by the mass of that. So, it is like a weighted average you can think about. So, if you have a group of chemicals out there and you are looking at one particular impact, so from that group of chemicals, say global warming potential, several gases are out there. So, if we want to quantify the total global warming potential, we will take the impact from each of these gases multiply by the mass of the gas or mass of that particular stuff coming out. So, that is how we do the summation. So, that is what it is being shown as in this equation at the bottom over here. So, let us look at, we'll do a math, and that will make it a little bit more clearer. So, if you have to do this global warming index for say 1,1,1 trichloroethane from a particular process. So, we have been say 1,1,1 trichloroethylene production process. So, we use as an industrial solvent, we know that it is a react, and for cleaning as a reaction intermediate, other important use, and but when we try to make them, there are certain things which gets emitted into the atmosphere. So, here at the bottom, the data that has been given to us for this particular problem, we have 3 chemicals are provided. Again, these are most of the times you see these lists are only just an example list. They are not the complete list of chemicals which gets emitted. Do not quote that only these 3 will get emitted when you are producing trichloroethylene. There will be some more, but these are the important ones. And let's so we have these 3 emissions, which is trichloroethylene, carbon dioxide, and nitrous oxide. We have the mass of it being released. So, kg per hour of say 7,760. Nitrous oxide 0.14, and we have been given greenhouse gas potential. This is the ratio. See the carbon dioxide, we have number 1. So, here this means 100 times more potent than CO2, and N2O is 298 times more potent than CO2. So, these numbers are based on with the CO2 as the baseline, as you saw in the previous slide. So, now if you have to calculate the global warming index for that, how we will do that? We use the equation which we just mentioned earlier, which is you take this groundwater greenhouse potential, that is index times the mass, and sum it up. So, here 10 kg per hour, and for 100 for TCA, then for CO2, and this is for our N2O, and if you add them up, if you look at here, although both TCA and N2O has much higher greenhouse gas potential as opposed to CO2, but CO2 just being so much of a mass, the most significant out of 8,800 numbers that you got for the total greenhouse gas potential for this process, the predominantly 7,760 came from CO2. So, that is almost nearly 90%. 90% of the impact is just coming from CO2 and rest is coming from others. And it's although N2O has a very high greenhouse gas potential 298, but the impact is much lower, even like less than 1% of the impact coming from CO2. That is why N2O, although in many processes N2O gets released, including in the composting process, but we do not see that much of an issue in terms of that much of a discussion on N2O when we talk about greenhouse gas potential. The reason being that is the impact is much less, as has been calculated over here. If you take the percent of process for each chemical, CO2 is 88%, TCA 11%, and N2O is only 0.5%. So, that is why although their impact is much higher, but since the mass is much less, it's the total impact comes out to be much smaller. So, similarly, and let us look at another example. Say if you compare electricity generation by the fuel type, there will be some emissions of gaseous pollutants coming out, and we can take emissions of the gaseous pollutants with different fuel types that is coming out, and we can classify them into different impact categories, and their potentials characterized. Finally, the environmental impact can be calculated from emissions and the impact potential data. So, if you look at with the next slide, we will look at for production of 1 kilowatt hour of each electricity type. So, if you look at here from cradle to gate, so we have hard coal, oil, natural gas, nuclear, hydro, wind, and photovoltaic cell, which is a solar power. So, for all these different types of potential energy sources, if you look at, again, these are not the complete list. So, this is a kind of some emissions. So, here dinitrogen monoxide and these are your units for hot, and for you see the emissions coming out for production of 1 kilowatt hour of electricity. So, here we can say, if you remember from the previous class, we talked about that functional unit. So, this is a good example of functional unit here. So, if you have to compare the different types of electricity production, you can take a functional unit of 1 kilowatt hour, or you can take a functional of 1 gigawatt hour, whatever, but it has to be the same for each of these electricity different types of electricity production system. So, for say 1 kilowatt hour of electricity being produced, so we have different emissions coming out. We have nitrogen monoxide, non-methane volatile organic compound, methane, nitrogen oxide, sulfur dioxide, and you look at all these different numbers coming out. So, what we will do with these numbers? So, what we will do with this number is we will calculate, and this is what happens in today's when you do the real LCA, most of these work is actually done by the software. But as a researcher, as a student, as a practitioner of LCA, you should understand what the software is doing for you. So, you just not take because software can always make a mistake, and if you input something wrong, or if you selected some wrong process, it will give you a garbage coming, the result will not be correct, but you should be able to know what is actually going on into the software. At least you should have a good idea of that. So, how we can go about this calculating that? So, if you want to do this global warming index, again this will be this calculations usually done by software these days. You can even use Excel spreadsheet to do this kind of calculations if you have a smaller type of LCA being done. So, here if you look at, we know the dinitrogen monoxide global warming, it's N2O 298, methane was 25, carbon dioxide is 1. So, these are the 3 which will contribute to global warming, and so, that's as opposed to NMOC, like NMVOC, sulfur dioxide, they do not contribute to the global warming. So, only these 3 will contribute, and we have this data. So, the inventory value for each pollutant will multiply using these equations. We know the greenhouse gas potential, we multiply it by mass. What we have been given in this particular table is the mass. So, we can do that, and if you do for hard coal, we found that for table entry, we can calculate it for the hard coal, and we get 113.52, and and so that's 29.01 times 298, and then converting from milligram to gram, we got 113.52. Similarly, you can do it for the others as well. So, you can calculate for others in terms of the greenhouse gas, and then you can add them up. So, here finally we got for hard coal this much, oil. So, if you compare the hard coal was the highest global greenhouse gas global warming potential, as if you say if the only category that we are worried about is the global warming potential, and in terms of comparing these different types of electricity production. So, this hard coal comes out to be the worst, because that is the highest value you see over here, that is your 1295, almost 1294.37, and then you go to oil, then you have natural gas, and then we have a photovoltaic cell, then we have wind, hydro, nuclear, and then hydro. So, hydro comes out to be much better in terms of global warming potential, but this is for global warming potential. It may not be the same for other impact categories. So, let us look at the other impact categories. So, in the other impact category for the acidification index, similar calculation, you get this acidification index potential 1.07 and 1, and these two, nitrogen dioxide and sulfur dioxide, is what will cause that, and you do the same kind of math over here, you get the numbers, and here you see oil actually comes out to be the worst. So, earlier our hard coal was bad for global warming, but for acidification oil is bad. So, we have to make a decision, and on which like how to do that, and the best one here is hydro. In the earlier one also the hydro was the best. So, best in terms of lowest acidification index was hydro, and its lowest global warming potential is also hydro. Smog formation, similar calculations can be done using this the factor. And for smog production, again the worst one is oil, followed by gas. Hard coal comes out to be the third one. So, it is not the worst one, it is actually the third worst. Hydro is the best, and nuclear and wind is potentially the same, and photovoltaic cell comes out bit after the hard coal. So, again you can see for the different types of impact categories, different process comes out to be better or less. So, what does that mean? That means that as a practitioner or as a policy maker, we have to decide which impact categories is more critical for me. So, among the different impact categories out there, which one is the most critical, which one which gives more weightage, and based on that we will decide which one is good for us. So, you do a weighted average and then you come up with which one is better. So, this again, it does not mean that oil is always better than hard coal, depends on what type of impact you are looking at. So, this comparison shows the electric generation is the highest impact, we already talked about that, and hydro, solar are the best alternatives. Nuclear also exhibit low impact. The problem with nuclear is the nuclear waste disposal, we have to be really careful about that. But other types of this, so these results can be used to make the informed decision whether to not purchase, whether you can go for that. So these are different environmental impact categories are there: greenhouse gas, ozone depletion, acidification and other things. These based on the cause and effect, we talked about that, and we look at our objective like physical and chemical and subjective factors. There are some methods out there which gives us a science-based indicator set for human and ecosystem health. This Tracy method, which is a EPA, US EPA developed method that is used, and there are other methods out there which is done as well. We talked about that recipe 2002 and other. So there are different pathways, 23 exposure pathways are taken and based on that this method has been developed. Toxicity is based on the cancer for the carcinogen and for and reference dose or concentration for the non-carcinogen. So here is some of these rankings of the different types of compounds out there, and this EPA human risk, Dutch human risk, Dutch aquatic toxicity, eco risk, toxic Dutch. So based on their different risk factors have been given for different types of chemicals and based on different types of impact that we are looking at. Then we also have to look at the social performance indicator, which we haven't. Again, LCA does not take care of the social aspect. When we talk about big picture life cycle, when we big picture sustainability, there the social comes in picture. LCA is mostly environmental. So, we have focused mostly in this course on the environmental aspect. We have talked about social little bit, but we have to look at the social concern in terms of the infrastructure, end user function, and the sustainability, what are the in terms of the how human aspirations and health, education. So, in terms of engineers incorporating this social responsibility in a formal fashion, it is always a challenging. There is a new methodology is still being developed. The first draft is out there. The United Nations Environmental Program and CTAC, they have come together and come up with a social LCA document out there. I encourage you to look at that document if you are interested, and I think initially in some of the lectures I kind of mentioned that document as well, but still it's in a preparation stage. We don't have out there. So, and then there are some social development indicators which have been used from that. There are different types of poverty, governance, health, education, demographics. Those things are used for that. So, if you look at, and this is again from the social sustainability stakeholders in terms of employee working condition, international community, future generation, consumer. So, there are based on the different types of activities. So, this is more of for you as a reading material. You go over that. We did not cover much of the social LCA because that was not part of this course, but there is something like social LCA out there. I just wanted to introduce you to that. So, this is the summary slide, and after this from the next video onward we will be focusing more on, I will give you example after example. So, I have several examples lined up which I want to go over in the next video. So, kind of a summary for this particular course. We as an engineer we play an important role in global sustainable development by developing and commercializing technology, and we are trying to improve the standard of living. We are and our goal is to have favorable economic return, but at the same time we have a goal to minimize the environmental impact and as well as improve the social conditions of a stakeholder. So, this particular course, we provided some of these principles to address the environmental issues. We even talked about some environmental economics aspect a little bit and give you a different environmental indicators, and also touched upon the social sustainability aspect. We did not went into detail of that. So, taken together, what I have tried to do in this particular course for this particular is try to give you a tool. So, this is one of the tool in your toolbox which can help you as a future engineer to design things more responsibly, especially from an environmental perspective. So, with that I will close this particular video, and then from the next video onward we will start looking at examples of how this LCA is used in real world projects. Thank you.